Welcome students. In this lecture we are going to discuss the complete unit 2, that is voltage source converters, and these are the topics included in this unit. And let us see the first topic is single phase 3-phase full wave bridge converter transformers connection for 12 pulse operation. So after that we will go for the other topics like 3-level voltage source converter, pulse width modulation converter, basic concept of current source converters, and the comparison of current source converter with voltage source converter. Let us see the single phase full wave bridge converter. So generally rectification converters and oscillating oscillating sinusoidal AC voltage source into a constant current DC voltage supply by means of diodes, thyristors or transistors. So we can use any sort of mode to convert AC to DC voltage with the help of diodes, thyristor or transistors. So this rectifying process can take on many forms with half wave, full wave, uncontrolled and fully controlled rectifiers transforming a single phase or 3-phase supply into constant DC level voltage. It depends upon your application. So let us see the single phase fully converter operation. So this is a circuit diagram which consists of 4 thyristors. So SCR1, 2, 3, 4 and AC input voltage. So at any time 2 of the 4 thyristors are forward biased, so while the other 2 are reverse biased. So input voltage is the AC voltage. As you know, this is a representation of AC voltage. The positive half cycle is up to 0 to 5, negative half cycle is 5 to 2 pi. So when the AC supply is given, the positive half cycle, this is a conduction of thyristors. See, at any time 2 of the 4 thyristors are forward biased. In each limb 1 thyristor will conduct. So here SCR1 and SCR4 conducts per positive half cycle. So this is the manner of flowing conduction. So SCR1 for positive half cycle in this way. So 1 and 4 through load, the load current will follow, and this is the forward conduction mode. And these two, that means in reverse bias, so these two are in open circuit. So these two represent like SCR. So these two acts as a short circuit. Sorry, this is open. This SCR2 and SCR3 acts as a open circuit for positive half cycle. Okay, and this is the output voltage for positive half cycle. So the output voltage you can see like this, and when from pi to 2 pi, and here for positive half cycle this is plus and here it is minus. Okay, so and for negative half cycle the thyristors, so 3 and 2 will conduct. Okay, so thyristors 3 and will 2 conduct means that is they are in forward biased, while the other 2 like 1 and 4 are in reverse biased. Okay, so at the time here we can see here, so 3 means this is the direction of current. This is the conducting mode. So the signs will interchange here. This becomes plus and this becomes minus. So because here the anode is connected to positive side, so from this you can see the direction. So you can see here, and this is the way of conducting, plus to minus. So if you observe here, the direction of current through the load, so both are in same direction. Okay, both are in same direction means here it acts also. The output from pi to 2 pi will get a positive half cycle. In this way, the cycle repeats and you get the continuous DC output voltage. So this, and for coming to three-phase fully controlled rectifier, in other words, you can call it as a bridge or 6-pulse converter. Here, 6-pulse bridge, 3-phase fully controlled rectifier, we can also call it a 6-pulse converter. The 6-pulse bridge has 6 valves arranged on 3 limbs. So for the vertical valve structure, so 6 pulse bridge has 6 valves. So you have 6 thyristors. These are the 3 arranged on 3 limbs. This represents your limbs. So this is limb 1, so limb 2 here, and limb 3. Thyristor 1, 3, 5. Thyristor 1, 3, 5 belongs to upper group, that is positive group or upper commutation group. So upper group, positive group or upper commutation group. Similarly, so 2, 4, 6 or lower commutation group or lower group or negative group. So phasor representation of these voltages, which is each phase is separated by 120 degrees. Phase sequence is R by B. And at any instant, 2 valves are conducting in the bridge, one for upper group and from lower group. See, suppose if T1 is conducting here from upper group, the 2 thyristors have to conduct at any instant, one from upper group and one from lower group. See, T1 is conducting from upper group, then T2 must be conducting lower group. Okay. So if 3 is upper group, so one of the thyristor and the lower group must connect. So that is the procedure involved here. And each device should be triggered at a desired firing angle alpha, and each thyristor conducts for 120 degrees. Here there are total 6 thyristors, 3 from upper group and 3 from lower group. So each thyristor, suppose if you want to conduct thyristor T1, it should that the thyristor conducts for 120 degrees. Okay, and the phase shift between the triggering of each adjacent thyristor is 60 degrees. That is, the thyristor must be triggered in a sequence. So T1, T2, T3, T4, T5, T6. Okay, so in that sequence, each thyristor will conduct for 60 degrees, and so each pair of thyristors will go for 60 degrees. Okay, so that is for alpha is equal to 0. For example, alpha is equal to 0. So T1 conducts at 60 degrees, and alpha is equal to 30. T1 conducts for 60 plus 30 is equal to 90 degrees, which we'll see to give more clarification when we step into the waveform. And there are certain assumptions to follow in this fully 6-pulse converter. So the AC voltages at the converter bus are balanced sinusoidal with frequency constant and lossless inductance. Okay. And the DC assumed is constant. The DC current is constant. The valves can be modeled as ideal switches with zero impedance on conducting, and zero impedance on conducting means there is no impedance, so there is no opposition, so it acts ideal switches. And infinite impedance when not conducting. So when not conducting, there should not be any flow of current. And ignition of values at equal interval of 60 degrees. So this could be your waveform. I will explain neatly. So first you draw the 3-phase waveform. So R phase, you can see this is 3-phase waveform, R phase, so Y phase and B phase. These are the 3 phases. And So invert these traces in order to get the line voltages. This is the inversion of R phase, inverting. Okay. So you can see here this inversion R phase, Y phase, and B phase. This is your B phase. And represent this. So each interval is, that is 30 degrees, 60 degrees, 90, 120, 150 and 180. So pi indicates here. So 0 to 180 degrees is your positive half cycle, and 180 to 360 is a negative half cycle. So you know. And alpha is equal to 0. So this T1, the triggering of T1, you can see this duration of T1 is 120 degrees alpha, because each thyristor should conduct for 120 degrees. Upper group T1, T3, T5. So each thyristor it is 120 degrees. T1. So T3 is 120 degrees and T5 is 120 degrees, 135. So you can see clearly here. So T1 conducts for a time period of 120 degrees here. The same representing. So T3 is similarly 120 degrees, and T5 here you can see 60 degrees, and here it is 60 degrees, total 120 degrees. So for alpha is equal to 0, the thyristor T1 conducts from 60 degrees, because the positive halves, the more positive will appear at 60 degrees, and the thyristors for alpha is equal to 0, and the sequence of thyristor is T1 and T6. For see, thyristor 1, so we are giving triggering at 60 degrees. This is saying alpha is equal to 0, means the thyristor trigger at 60 degrees. Okay, so 60 degrees means it acts as T1 through a load and T6. So the phases for upper T1 thyristor is R phase, and for T6 thyristor is Y phase. Okay, so you can see in waveform R phase and Y phase. So T1 and T6 are conducting. Okay, and this could be your T1 and C6 conducting, and the same way represent, the same will appears as output R and Y. Is it clear? R and Y. Okay, so always we consider the most, that means the, so positive, the positive wave, the more positive wave and the more negative wave we consider. The more positive in upper group and more negative in lower group. Okay. So after this, again the T1 will conduct for T2. So because this T1 should conduct for 120 degrees and each pair will conduct for 60 degrees. So T1, T6, this is the output waveform, and again T1, T2. So the phases, T1 is connected to R phase and T2 is connected to B phase, C. So after that, this is your T1, T6 and T1, again T1 to T2. So here T2 is connected to B phase. So thyristor to T1, T2 Again 60 degrees is connected to B phase. This could be your more positive of VRB, and the output appears as it is VRB. Okay, so the full conduction period is over for T1, and again after in positive group T3 will conduct. Similarly, this T2 in lower group, it should also conduct for 120 degrees. This T2, so the sequence of order T1, T2, T3, T2 should also conduct for 120 degrees. So 60 degrees with T1 and 60 degrees with T3. In this way, you will appear the output waveform. So again, consider the most positive, the upper group, and this could be your more positive, and the same will appear as output. So this is your 6 pulse or 3 phase converter for alpha is equal to 0. Similarly, if you take alpha is equal to 60 degrees, the thyristor will conduct with the thyristor T1 will start conducting at alpha is equal to 60 plus 39 degrees. Okay. So you will get clearly, and if you want more the graph, see here again 60 degrees, this is your more positive. For more clarification, I have presented one more graph. So for alpha is equal to, you will see for alpha is equal to 30 degrees, 60 degrees. So for alpha is equal to 30 degrees, you can see 30. So it starts at 90. I told you alpha is equal to 60 means 60 plus 30 degrees means 30 plus 60, it is 19. So this is your most positive. So till it conducts, okay. So the output you will appear as it is up to 150, and again the other thyristors will conduct the same, you will get. So you can see the output. In a similar way, you can go for alpha is equal to 30, 60, so 90, 120, 150 and 180. So alpha varies. The range of alpha is 0 to 180 degrees, and the output voltage can vary from plus VD0 to minus VD0. VD0 represents the output voltage. So thus the same converter acts as a rectifier or inverting depending upon DC voltage, so positive or negative. So you can plot the graphs for alpha is equal to 60 and for alpha is equal to 90 degrees, etc. You can refer the textbook TS Bimra so that you will be more clarity. Okay. So operation of 12 pulse converter. So the 12 pulse converter is constructed using two 6 pulse. So before that, why we step into 12 pulse converter? We have some 24 pulse converters. More number of pulses if you go, then we can, so output voltage will be, you will get more smooth constant DC output voltage. So if you increase the number of pulses, so you can reduce the harmonics, and at the same time you will get the constant DC voltage, so pure DC voltage. And 12 pulse converter is constructed with using two 6 pulse converter connected in series and phase shifted by 30 degrees through star-star and star-delta transformers. The two 3-phase star-delta and star-star transformer sources set the supply for 6 pulse bridges phase displaced by 30 degrees. So you can see here, so this is your star primary side and secondary side, two 6 pulse bridge converters. Star delta is your 1 6 pulse. So this is 6 pulse bridge converter as we seen in the previous slide, the output graph. and this is your second 6 pulse converter which are connected in series. So star delta and star star. So the reason for why star star and star delta configuration is to achieve 30 degrees phase shift in the AC voltage waveform. Okay. So if you connect both star star means you don't get 30 degrees phase shift. So to achieve 30 degrees phase shift in the AC voltage, we connect the two in this manner. That is, two 6 pulse converter bridges are connected in such a way that 30 degrees phase shift displacement is obtained between the two secondary 3-phase AC voltage waveform of two transformers. Okay. Secondary side, you will get 30 degrees phase displacement. It's between the two secondary 3-phase AC voltage waveforms. So the 6 pulse bridges are in series to increase the DC voltage, and the two transformers on the AC side are fed from the same 3-phase AC source. So however, to obtain 12 pulse that are symmetrical phase, it is displaced by 30 degrees. So one is connected to star and one is connected to delta. So the use of 6 pulse converter is preferably over the 6 pulse converter because of the reduced filtering requirements. We can eliminate the 5th and 7th harmonic by 12 pulse converter, and this could be your output voltage waveform. So simply I am showing the output voltage because the same we will get if you add two 6 pulses, you will get the 12 pulse output voltage. So one of the advantages, the phase shift of 30 degrees is utilized to eliminate the AC side harmonic currents of order 5th and 7th, and also to eliminate DC side, that is 6th harmonic voltage. And by adjusting the tappings on star connected transformer, the converter DC output voltage is also controlled. And one other advantage is the short circuit current through any of the thyristor is controlled by leakage reactance of the transformer, and the reactance of the converter transformer helps also to reduce the harmonics. That means it assists the harmonic suppression. So if you increase it, you can see here high pulse rates. So typical phase angles and phase shift in multi-phase systems you can see in this table. So pulse count for 6 pulse, you can see the phase difference is 30 degrees, whereas 12 pulse the phase difference is arranged in a manner of secondary side is 30 degrees. So if we go on increasing the pulses, this would be your phase difference. Okay. So increasing pulse number means you will get output. You are eliminating the harmonics, and you will get the constant. That means ripple free DC output voltage. Okay. For this, you can use the phase shifting transformer in order to make the phase difference with a single primary winding and several secondary windings. So the secondary windings are interconnected in such a way to give a resultant waveform that is shifted in phase from the primary waveform. So in order to make this phase difference, we use the phase shifting transformer. So as pulse count increases, we get the ripple free output voltage. This is about 12 pulse configuration, 3 single phase fully controlled and 3 phase or a great circuit or 6 pulse converter. So next class we'll discuss the voltage source converter.